Suppose we have the probability of A and the probability of B. What's the probability of A union B? Now, we've already found these probabilities using tables and Venn diagrams, so we don't need a separate formula for it. But remember, if the only tool you have is a hammer, then you have to treat every problem like a nail. So let's introduce one anyway. So suppose we have a two-way table where we have our events A and A complement and B complement, where they occur certain numbers of times. So we can find the probability of A and the probability of B. And we can also find the probability of the union of the two events. So let's take a look. The event A union B occurs P plus R plus Q times, and we can view this as the event A occurs P plus R times, and there are Q more times that the event B has occurred. Or we could view it another way. The event A occurs P plus R times, the event B occurs P plus Q times, and both events occur P times. So there are P occurrences that are counted twice. So the correct number of occurrences is P plus R, the number of times A occurs, P plus Q, the number of times B occurs, minus P, the number of times they both occur, out of our total of P plus Q plus R plus S times, and that gives us our probability. And finally, if we divide this by our total P plus Q plus R plus S, we get the expression. And here we have the probability of A, the probability of B, minus the probability of their intersection. And so this gives us a formula for the probability of a disjunction. Again, to really understand something, solve it again. Since we know how to find the probability of mutually exclusive events, the Venn diagram suggests A union B can be split into three mutually exclusive regions. The part that's in A and not in B, the part that's in both, and the part that's not in A but also in B. And so this event A union B, we can write it as a union of mutually exclusive events, which means our probability can be written as that sum of the probabilities. So you can get anything you want as long as you pay for it. The first two probabilities give us the probability of A, because something in A is either not in B or in B. The third probability gives us part of the probability of B, and the part we're missing is the probability that we're in both. So we'll need to add that probability, but to pay for it, we'll subtract it. And again, this gives us the probability of A, the probability of B, minus the probability of their intersection. For example, suppose we know the probability of A and B and the intersection, then our formula tells us the probability of their union will be and in a kind and gentle universe, we'd always be given three of the terms in this formula. We don't live in that universe, but we still have to solve problems. So, for example, let's say the probability the meal is fish is 0.4, that's fowl 0.5, and the probability it's neither is 0.2. So if F is the probability a meal is fish and W is the probability it's fowl, then we have our probabilities. Now, if something is neither fish nor fowl, then it's not fish and also not fowl. And so this corresponds to this intersection of the complements, and we have that probability. Now, while we're at it, let's go ahead and find the probability of the complement of F and the complement of W, and these will be, and now we have two events and their intersection, which are related to the union by our formula, And we can substitute in our values to find